Hey everyone, today we're going to finish all that I want to talk about in chapter 5. We're going to be moving on to this next little section about the center of mass. So let's say that, for all of the problems that we've done so far, it's been focusing on a single object. It was a sled in many of my examples, or it could have been a ball thrown through the air. It's just sort of we're looking at a single object in these cases. What if we want to look at something a bit more complex? Maybe this shape of this object is very, abstract, and it uh, has a lot of edges that go far out. It's hard to describe how this thing may move, or maybe it's not just a single object. Maybe it's uh, a cluster of many objects sort of tied together. All right. Hey, come on in. So today we're going to go over um, the center of mass. We have gone over um, singular objects before, a ball thrown through the air. Um, Perhaps maybe it was just a sled or something sliding on a table. What if we want to look at a system of more complex, pieces? Maybe there are two sort of large objects that are tied together somehow, or maybe there's an object with a obscure shape. So we're going to find the center of mass. Now let me bring up my little diagram. We have on the right here, this is just, think of it just sort of like, two spheres, or maybe if you wanted to think about them as planets or what have you. These two objects are some distance apart from one another. Let me actually zoom in a bit. Actually, I don't want to get rid of, I'll go like that. Okay. What is the center of mass in these situations? Well, let's, write what we know beforehand. I'm just going to always call one of them M1. We'll just say the one on the left is M1 for all the cases, and the one on the right is M2 for all of the cases. And the very center of these spheres is the center of mass of the object. So typically, in a ball or some sort of regular shape, the center of mass is going to be in the exact center. You think of it as if you were to squish this object down to a single point, where would that point be? In a sphere, simple, it's right in the exact center. It'd be the same thing if it was like a cube or, some regular shape. If it was a sort of like a ruler, or, some sort of tube or rod, center mass would likely be in the center as well. So in these cases, these are in the center. Here, what is the center of mass of the entire system, though? So that's where we need to start defining not just where the masses are, in space. We need to refer them to the distance between each other. So let's label this. I'll just say this is x1. So this is at position 1, pretty much is what I'm saying. And this is going to be x2. That's going to be the same for all of these. So let's, oops, sorry, this is x1. That is x1. 2x2. Okay. Now this may not be the case for, whatever problems you're given, but I can choose where I want to, you know, start my coordinate system. So I'm going to say x1. I'm going to refer to all other things in the problem to x1. So I'm going to say x1, the position of this particle is 0. So that's sort of like the origin point. That may not be the case in your problem that you're given. Maybe they say um, 0 is, a wall over here, and then you'd have to actually find a distance to, each individual thing that way. So in this specific example that I'm doing, I'm going to say x1, the position of all of these first particles is 0, 0, 0. Okay, and then this is where we would want to find, relative distances between whatever's in our problem. So just the distance between these two. So that's fairly simple. That's just the difference, like that. Difference of their position. Now, before I, finish off this picture, let me write sort of the equation for the center mass. So maybe we have one thing over here, one thing over here. We want to find the center mass of both of them together. So we're just sort of like lumping them together in the same picture. Previously, I'd draw like a free body diagram. I'd make a dotted line around what I want to look at. In this case, you imagine I am wanting to cluster these two together. So in this case, we have this capital M is times the position of the center of mass is equal to, this is, capital M, lowercase m. This is mass 1 times the position of the center of mass of, particle 1 plus m2 x2, like this. And I'm going to say where this capital M that's just the total mass of whatever I'm looking at. So whatever the system is, that's the total mass. M1 plus M2. Total mass. Okay. Now from this equation, I can rearrange it a bit to just find the center of mass location. So how far away on this dotted line is the center of mass? It will be, since I'm going to call, I'm going to skip some steps. So you hopefully see, since I'm calling this 0, x1, 0, let me connect these zeros. This first term will go away. So that's why I'm going to write that the position of the center mass after I divide the total mass over is m2 over total mass times the distance between the two objects. And we know capital M is just the total mass. So I'll rewrite it like this. So we have a way to find the center mass, if we can find out a little bit about each individual particle's position already. So I say this one is right here. This one is known to be over here. I know what their masses are. Then I can find where the center of mass of the entire system is. In my picture, it's basically me saying, since these two things are the same, it makes sense that the center mass will be sort of in the middle. As something becomes more massive, so as M1 gets larger, this term grows. So this center of mass position may change, may drift towards, or I guess I should write that mass 1 will change down here, and that's how you see the position may change. It'll drift towards the larger mass. That's, and even more so like this. This is actually what's happening with, say, like the Earth and the Moon. The Earth is massive. It's huge compared to the Moon, but the Moon still has, I think it was like a third the size of the mass of the Earth. In any case, the center of mass of the system, if I looked at the whole system of Earth and Moon, the center of mass isn't right at the center of the Earth. It's sort of drifted up a bit, kind of towards sort of like the crust of the Earth. So that would be center mass of that system. Let's sort of take this sort of theme right here. This was for the center mass in one dimension, sort of just horizontally. I forgot to say that, moving to the right is positive x. Something that's kind of given already. So we have this sort of method. Let's just take this and run with 2 and 3 dimensions. Let's go like that. So first off, we saw this, work with 2 things together. Let me write it out, an expression that would work for as many items as you want. So, not just 2, it could be, thousands of individual little particles together. As long as you know the position of every single one in relation to every other one, you can find the center mass of this system. So let me write it out like this. So total mass times the position of the center mass. This is in 1 dimension. M1 x1 plus M2 x2 plus M3 x3 and so forth. See, this could go on for as many objects as I want. So I'm just going to say M n. N is just whatever number I'm going to stop at, times xn. So this could be up to, M20 and x20. I'm just adding each individual one together, whatever the problem asks for. But you see, this is just for 1 dimension. This also works for 2 and 3 dimensions. So let me summarize that with this. So you see, this is just sort of a summation of all the objects. So let me rewrite this up here. And try to keep this clear. Equals the summation. So just like what I have above of mx, these are I, these are sub I, like this. So what this means, this is basically just saying this. So however many objects, particles you have, you're just going to add up each one separately, just like we have up here. That's for one dimension. You can do it for two. Oh, not capital Y, it's a lowercase y, m. So there's a center mass in the vertical direction as well. Same exact equation. And we can do it for 3 dimensions. So since we can do it for X, Y, and Z, remember how we could kind of relate those coordinates together, to make it 3 dimensions. What was the relation there? Let me move this down like that. I'm gonna run out of room. Let me shrink it a bit. So remember that, let's say like remember when dealing with 3 dimensions, we were finding just a position vector that combined all 3. That was R vector. And that's just, X, magnitude X in the horizontal direction, magnitude Y in the vertical direction, magnitude Z in the sort of height dimension, I guess, 3rd dimension. That's just the position vector. So maybe you see where I'm going with this. I'm just going to write the same exact thing, but now dealing with 3 dimensions all combined together with this position vector. So we have, make more room. It's going to be like this. That is just, mass 1 times position vector 1, mass 2 times position vector 2, and so on. This just becomes a summation of however many things I want to find in 3 dimensions. But now maybe you see that this can become out of hand very easily, because I personally don't want to find a position vector for over like 10 things in a problem. That becomes way too much, way too quickly. This is where, we're summing up, many things. If we have a large sum, that is basically just an integral. So if this is an object, say it's not, 2 particles or 2 spheres. Say it's, a continuous flowing object that has many thousands of particles in it, and we need to find the position and mass of each one. This is where we would it'd be way more helpful to integrate. just a bit. So I'll write this down and we'll do a little page on integration in a moment. So this is just the integral of the position vector, with each individual small slice of mass. All right, so let's do an example that doesn't require an integral right now. So example, find the center of mass of the uniform sheet of plywood shown below. So we have this sort of oddly cut piece of plywood, and it's got in some, at least manageable sections for this problem. We want to find the center mass of the entire thing. Where is it going to be? What are the coordinates of the center of mass? What's the x coordinate? What's the y coordinate of the center of mass? So we need to find first off, we need to find a place to call the origin. I'm going to call the origin. So I'm going to call the origin right here at the bottom left. So you see I'm making sort of a Cartesian grid. Y, like this. So that is the origin of choice. Now let's maybe slice up this shape into some more manageable shapes. A lot of problems become easier if we simplify. So let's cut off a slice of this sheet. So an easy thing to do is just slice this small bit off like that. Now you see there's this weird shape is just made of two simple shapes. We have a rectangle that is shape 1, and we have a square that is shape 2. Now, is it exactly a square? Well, so this length is 6.6. That is 0.8. So turns out that this top little bit is, 0.2. Which means that this is exactly a square up here. And that means that this is also over here. That's, this length. In any case, we have these two shapes. We can find the x and y coordinates of the center mass for each of these shapes added together. So let's split it up. Let's first start with the x coordinates. So I'm going to say x center mass is equal to 1 over capital M, so total mass, M1 times x1 center mass, or I guess I can keep it consistent. for later. Let's say center mass 1 plus M2 x center mass 2. And over on the right, I will put the y section, the vertical section. Same exact thing, except in the vertical direction. Okay. There's a problem. Maybe you see it. We aren't given a mass of the total object, and we're not given a mass of each section separately. So how do we find the center mass at all? Well, they do give us in this problem description, they do say that this is a uniform sheet. So that means it's something with a constant density all the way through. So if it was a regular shape, we could expect the center mass of that regular shape to be in the middle. But this is me trying to, just find the area of these shapes. In fact, I can relate the area of the whole thing. So the whole thing, that's probably just not helpful. The whole thing over, as a ratio of each individual piece. Let me just show you. So instead of, I'm going to be putting instead of mass 1 over total mass like this, I could do it as a ratio of the area instead, because I'm given plenty of information to find an area. So instead of doing or dealing with masses, we aren't given a mass, I'm going to use the area instead. So hopefully you saw this 1 over m would be m1 over capital M, or m2 over capital M. So instead of doing that, I'm going to do area 1 over total area times, center of mass 1 plus area 2 over the total area times center mass 2, like that. So hopefully that jump to just, getting rid of mass altogether was at least somewhat clear. Since we're not given a mass, I'm just going to assume that mass and area can be interchangeable in this case. I feel at least confident with it because it says a uniform sheet up here. So that's for the horizontal, same thing for the vertical. 1 over A. Oh, sorry, it's A2 over A. Okay. So we have some, areas to find or to calculate, and we have some, small center of masses that we could maybe find with just the geometry. So let's do that. Let me keep the picture in the frame like that. So the area of this first bit, this first shape, this big rectangle here, I'm going to say is, I've already done this. That turns out to be 0.32 square meters. And I've already calculated this area over here of, section 2, and that is 0.04 square meters. This turns out, I could do this ratio that is in each term. So I'll just say A1 over A, just the area of that first section, divided by the total area is 0.88. I think the 8 just continues. And then area 2 over total area, something like just 1.111. I'm just going to leave it at 3 decimal places. All right, so we have these ratios. Now we just need to find these individual center masses. Since these are uniform, it's uniform density, and they are, manageable shapes, I can reason out just from measurements where the center mass of each large shape is. So the center mass of this large shape number 1 will be in the center right here. So it'll be halfway of this width, and it'll be halfway of this height right here. We go like this, keep the picture in the frame. So I'll just say by measurement, we get that the center mass just for that first shape in horizontal direction is 0.4 meters, and the vertical center mass for the first shape is 0.20 meters. Second shape, that is just a square up here at the top. So center mass of this is going to be the exact center. But remember, I'm calling the origin right here. So what is this? It will be 0.7, from here to here. Let me get rid of that. And I have to remember that it is this height from the origin that I've labeled in the beginning. So let's write that out. So it's going to be 0.7 meters. This is going to be 0.50 meters. Okay, so we have all of the pieces. We have these ratios, that and that. We have the center masses of each separate little piece. We just put these into the large equations up at the top. We get the overall center mass of the object has coordinates of, right at the bottom. Overall center mass 0.43 meters, and a coordinate vertical direction 0.23 meters. Okay, so hopefully, just some of this reasoning going through this, odd shape. It's one solid object, but it's made of, a couple of manageable shapes. That's how we're able to find it. So if I was to put the center mass, let me zoom back in, or no, I'll just do it from right here. So the center of mass of the large rectangle, I'd expect it to be in the middle, right? The center mass of the small square, the center right there. So where is 0.43? 0.4, 0.43 right there. Where is 0.23? That would be, there's 0.2, 0.23. Right there. Just make a big old dot right there. So that is the center of mass of this odd shape. If I was to, if I wanted to balance this board on, say, like a pin, or hold it up with just like my fingertip, I would be able to hold it up and balance it from right there, that center of mass. Okay, so let me get rid of those. I'll leave the dot. Why not? Just total center mass. Okay, so that's this problem. Let's move on to integration. Just the integration method so I could show you guys. I don't think I'm going to have any problems that involve integration. The manner of my quizzes and homework, I'm just showing you the integration method for other future problems you may have if you're going to go into any sort of engineering or construction. Let's bring that up. Okay, by integration. So we had fairly simple shape in that example. Even though it was a little odd, it was arranged in a way of manageable pieces, a large rectangle and a small square. Sorry, let's go like that. What if the object we're trying to find the center of mass for does not look as nice as that did? What if, it's a large arc of, a metal beam that has, a curve in it? Where is the center of mass for this thing? Imagine I could just cut out more shapes of that plywood example. I could put a big triangular hole somewhere, and maybe, very quickly becomes more difficult. So we may need to sometimes find the center mass through integration. And the example I'm going to do is going to be fairly easy as well for this. So we have, oops, sorry. So we have that equation we were given, or sort of left off at on the other page. Center mass 1 over the total mass, which is just an integral of all the small little position vectors for each little thing in this object. if it's like that metal rod, it's curved metal rod, we're going to have to sum up all of the tiny little mass particles of like iron in this object. So these are the individual small, infinitely as many mass particles. These are the position vectors for all of them. So that's where I go to this. For this example we're doing right now, it's just going to be a simple picture of just a uniform density thin rod. And I've placed it sort of off center. So I have one side of it at the origin right here, and the rest of it is just going out to the side. Now, a reason for this might become clear in a bit. I'll sort of bring it up when I get there. Why this and why not have it sort of positioned in the center? Like this. I'll bring that up in a bit. To start out, we need to look at this picture and sort of reason what we're trying to do. Let me try to reason through this. So we want to find a slice, just a small slice of this this thin rod of uniform density. So this thin slice, we're going to look at all of the particles in this slice, and all of them have some sort of mass that are in this little blue slice that I have right here. So I'm going to take a slice here, I'm going to take a slice right here, another slice right here. You see how they just sort of add up. Each individual infinitesimally small slice is dm, like this. And each of those mass particles has a density. So this lambda right here I'm going to write is density, linear density. Since we're only going in one dimension, it's only going to the right. The linear density times however far you're moving along the x-axis. So say I'm doing this slice right here. From the origin to that slice is a distance x. And how wide the slice is, that is just dx. So throwing up a lot of terms like dx, dm, lambda for density. This is where let's rewrite that equation from above. So we have center of mass of this position vector. Center mass, or the position vector to the center of mass of this whole thin rod. That's what this is. So it's equal to 1 over capital M. So just like above, we can change out the value though, since I've said that this is also, actually, no, we're not changing out the value quite yet. Let me like this. Since we are moving in the x direction, that's what I'm trying to get at. I don't want to I don't want to have an x and an r, so I'm just going to from now on call it x. That's what my notes say, and it's moving in the x direction. This is me just saying I'm only looking at one dimension. Okay, so since the mass is distributed from 0, the origin, to however long this sort of bar is, right here is L, capital L. Since it has a uniform density all the way through, let me write this down as I go. The mass distribution or sorry, no, I could keep that. The mass distribution is from 0 to L, capital L, just for however long this thin rod is. Also, what I could put down is that the ratio dm over dx is mass per length. So this is just mass, a little bit of mass over a little bit of length. Is mass per length, per unit length, I guess, let's say. And something about mass per length is that is exactly what density equals. So I'll write this, say so. Equals lambda dx. So that's sort of what I jumped to already with this picture. If we take a little bit of mass over how much distance it covers, that's a linear density. In 3 dimensions, density is mass per volume. In 1 dimension, it's mass per length. So let me go like this. There. Now moving on, we have a lot of things that we can do from this point. Position vector is 1 over total mass. Since I, up here, I put in a I hat. This is just a labeling of which direction is this pointing. So it's not going to change at all. I'm just going to bring that out front of this integral. So we have x dm. Okay. Well, what was dm? Dm right here, I said in the line above, is lambda dx. So let me just put another equal sign. And this is where we can introduce our limits of integration. We're going to integrate from 0 to L. And this is where I switch the dm into this. lambda dx. So this is the linear density times a tiny sliver of length. Hopefully at this point, now that you see that these are the limits of integration right here, are 0 and L, maybe now you can see that's why I have arranged the rod this way off center. So let me do a little sketch. I'm going to erase in a bit. So if I put the rod in the center like this, it would have been from minus L over 2 to L over 2. And so then our interval of integration be minus L over 2 to L over 2. If we were to do this, maybe you know already, this integral would collapse to 0 because it's even on both sides. So it's just going to subtract itself by doing this. So that's why I didn't arrange the origin in the center of the rod itself. Maybe that's clarify that. So that was a little side note. Where are we? We have something else to sort of realize. We have this mass, capital M, just hanging out front. Well, let's look at what that equals. So instead of the total mass of the whole thing, we are breaking it up into very small chunks, very small slivers. So what is the small sliver of mass? So I'm going to say the total mass of the rod is just adding up all of the very infinitely small slices of mass. So you add up all of the small, if you add up all of the slices, you get the whole thing. Like this, right? But then it turns out I also have that equation that I've written above for mass, how it's related to density. So let's write that one out. So now we're going to have this integral out front and an integral right here. Let me shrink this down a bit. I need just a bit more room. Okay. All right. We know that the density, so there's going to be a lambda density right here. There's going to be a density right here. In the problem, though, we were told this is a uniform density rod. So this value right here and right here, that's just a constant number. Since it's a constant, we could pull it out in front of the integral sign. So let's do that. We know density is constant. So I'm going to pull it out front in both of these equations. So we have this. So this is sort of that, leaving off from right here. And that will turn into really just a factor of the length of the rod, the total length. M is the density. And this is all just in one dimension. L over 2. And I'm going to run out of room just barely. So let me. Okay, so again, we'll say again. Remember, M is lambda 0 to L dx lambda L. So this is like the same exact step as this. So we have the position vector one over the density of the length of the rod. Density times length of rod. Then we have to bring that new lambda in. Oh, sorry, that was down here. This lambda up here is from the original in the direction of, x, horizontal direction. L squared over 2. All of this shows us very thoroughly that the center mass of a uniform density rod is halfway through the total length, which is something that, we could arrive at geometrically, just measured it, but maybe, just maybe, some problems out there in the real world, the density isn't always going to be constant. Maybe you have, you're making like an awning, you're building something that needs to balance, and you know that part of it is wood, part of it is metal. It's got this different density as it moves along. So there is a reason for this. It just so happens that on this very simple example, the center mass is right in the center. Okay, so that's sort of me, bringing you to the the gate where integration is for finding center mass of some object. There's an example in the book that goes right after this step that finds the center mass of the next step in the book is find the center mass of a uniform density rod, but it's shaped like this. So where's the center of mass of this object? Y, X, and there's the rod. But the object has a sort of a bend in it. Where's the center of mass? Where is it? In this specific case, it's not even on this object. The center of mass will be somewhere right here, floating out in space. That's why on some of those, you might have seen like physics toys, or it could be like a bird or something. It's balancing on its beak, and it has a center mass that's outside of its own physical shape. So a lot of applications here, and we're just sort of barely approaching it. I don't think I am going to give that complex of a problem, of specific arrangements. We've already done this simple uniform rod. So I really just wanted to show you guys this part. Let's move on to the last little bits for what I wanted to show you in chapter 5. And then we're basically finishing chapter 5 today. I'll call it like a half chapter because we only have done 2 sections for chapter 5. So we did like friction, and I only wanted to cover center of mass. Okay. Next up is just probably one of the more simpler realizations. Since we've done so much already with motion, and then we're adding center of mass to the problem. Let me zoom in. So we're able to describe the motion of a system of many objects. Beforehand, it'd be the motion of just a single object, but maybe through doing all of this example work I've done today, you can see that I can find the motion of many objects grouped together by just finding the movement of the center of mass of the cluster of particles or objects. So let me first say that I can find the position vector for each object in the system. So that was total mass. Position vector, how does that change over time? Center mass. That's really just each individual object. How does it change over time? How does its position vector change over time? That first one, how does that second one react over the same amount of time, and so forth. On and on and on. This means that I can describe the motion of all of these position vectors just by adding them up one at a time. Okay. We know from chapter 2, chapter 3 also, that the change in distance over time is the velocity. So doing this, I've listed it out for each individual object and thing. This just shows me that's also, I could write it as, say, which is, so total mass times the velocity of the center mass. It's just the first object's center mass velocity. I'll just say the first object's velocity, second object's velocity, plus the third object's velocity, mass times velocity. That just is the summation of however many things I'm adding. Okay. Since there is this velocity, maybe there could also be a change in velocity as time goes on. That leads to me realizing it's the same as finding the acceleration. The acceleration of that mass times acceleration of that first particle plus mass second particle times its own acceleration, third particle, and that acceleration that it's feeling. That's just summation of all of the masses and all of the accelerations. And from this, was it chapter 4, we learned, just barely. Chapter 4, just like that, we learned about Newton's second law, which was mass times acceleration. So we have, go down like this, mass times acceleration right here, which means that I can figure out how a system of particles, two planets, orbiting each other or whatever, I could figure out the force, the force needed to accelerate the system just by learning how the center of mass is going to accelerate. So let me jumping from this step right here. So that's me adding up all of the forces acting on all of the particles within the system. So I'll say in general, I'll go in general. I'll say that's force net external. Let me go down like this. Is equal to summation of all of the small external forces times mass, total mass, times the acceleration of the center of mass. Let me, right, so this is just me saying, if you add up all of the small tiny forces acting on all of the individual particles, you can figure out how the center of mass of the system is going to move. So I'll leave this as say total external force on the system. And I'll say right here, I'll say each individual external force. Total mass of the system. times, say like times acceleration of center of mass. Okay. So say I have a dumbbell in space. We have, a dumbbell for, weightlifting. And I'm just floating out in space, nothing affecting me. I'm holding it in front of me. And I push one of the sides of the dumbbell. And we could assume the thing in the middle is massless. It's kind of like, think of it as just like a small massless thing connecting these two objects. If I force one side of the dumbbell, you can maybe expect it to start to rotate. But if I apply a little force to the bottom one and a little force to the top one, I can find that the acceleration of the center of mass, which will be in the middle where the dumbbell sort of handle is, will actually start to move in the direction of that force. For example, I don't have a picture ready for this, for that analogy, but maybe you could kind of picture it in your head. Also, if we just think about like a cluster of particles, or maybe that's that plywood board with a weird shape cut out of it. If I were to move, or if I was to add up all of the forces acting on, like pushing it, I could describe how that center of mass would move. Basically, once I find the center mass, I can describe how the entire object is going to move. Okay, so just a little bit on the motion of the center of mass. Other than that, it's pretty much all I have for today. So we finished my half chapter, chapter 5, on friction and center mass. Up next on Monday, we have a quiz that's only going to be on chapter 3 and chapter 4. So what was it, like motion in 2 and 3 dimensions and Newton's second laws. Sorry, Newton's laws. That's chapter 4. So I'd say take a look at the homework. Make sure you guys understand it. And I think I'll be here if you have any questions. Otherwise, have a good weekend.